Hello and welcome. So in this video, I will be implementing a BERT classification, especially multi-level classification model using the BERT. Now we all know what BERT is. BERT is basically a transformer encoders, a stack of transformer encoders which extracts contextual as well as embeddings from our input sentence. So it basically a transformer encoders. Okay. So if you want to deep dive into what our BERT is basically, so just go to this link. So this guy has explained in a wonderful way what BERT is and what transformers are. So I'll provide the link in the description of this video. Just take a look at it if you want to deep dive in the working and implementation of BERT and transformers. So yeah, without wasting any time, let's further dive in. So in this video, I will be implementing a multi-level classification. Okay, so I have already uploaded the data to my Google Drive here, train.csv and test.csv. We won't be using test.csv in this tutorial, but I'll be explaining on this data only. Okay, so we will split it into train and test. Okay, so let's go. We should connect our Google Drive onto our Collab notebook. So for that we need these two statements. Okay, from google.collab. I'm so sorry. Okay, so I'll just okay, cool. So now my drive was already mounted as I was implementing it earlier. Okay, so now what we need to do is first we should check what GPU we got for our collab session. So we got a Tesla T4. Okay, I should just restart my runtime, factory reset runtime, and I'll just okay, now I'll run it again. So I'll just use my account on which I have uploaded my dataset. Just copy the security code and paste it in. Just press enter, and then your Google Drive is successfully mounted on your collab session. Okay, now if we check what GPU we got, again Tesla T4 and 0 used. Okay, so next step is to install the transformers library provided by Hugging Face Transformers. It is an absolutely amazing library if you want to implement BERT on your own dataset. Okay, so I'll just write install. So this command will install transformers library provided by Hugging Face onto our collab notebook. So I'll just clear my output. Okay, so next step is to import necessary libraries. We will need pandas, we will need numpy, we will need torch, obviously, because we are going to implement it in torch. Shooter, and we also need sys. This we will be needing when we will save the checkpoint of our model. Okay, just don't worry right now. Okay, so this is my drive mounted on my collab notebook. So here, sorry, not here, and this is my, I'll just copy my path and I'll just say train path. Oops. Okay, and test path is same but test. Okay, next step is to load our data. Okay, so train df train. Okay, so that should load our data in our collab notebook. Okay, so let's take a look at what we got. Okay, we got title, abstract, and we got 6 labels that we need to classify. Okay, so we have a title and we have an abstract. Title is basically what does your abstract means, right? The basic title, like the news headlines, right? So the more data is in abstract, and only the title, which is like 20 characters mainly maximum we have title. So we have 3 approaches. So we could only use title and then train it against all these labels. We can use abstract alone, and then we can train it against these. And third approach would be to add these two and then train against. That would be optimal solution, because we want to train BERT, right? So it needs a huge amount of data. So in this video I will be joining these title and abstract into one column, and then I will be training against all these 6. Cool. Okay, so I will be doing the same thing, like I will be combining these 2 columns into one. So for that I'm gonna do this train df. I'm gonna create a new column, let's say context, and we're just gonna title plus, and I will separate it with a dot operator so that it creates it with a new sentence. Train df abstract. Okay, I think that's a okay. Now as we have combined these two, we don't need this column, id column, and these 2 column, right? Because we already combined this into context. So I'm gonna drop those columns. Okay, so let's see, first we have which columns. Okay, we have these columns, right? So we are going to just okay, train df is train df, and I'm going to drop, actually I'm going to drop these column first. Drop title, abstract, and id, right? Oops. Yes, labels is axis is 1 because rows are 0s and columns are 1, and in place is 2. That will drop our all these useless columns. Now I'll just rearrange the columns, okay, so that context comes first, because right now context is at last. It's just visually good. See, the context is last. I just want to replace it with, I just want to rearrange so that it comes in the beginning. So for that I can do is train df, and I'll just put my context first and then all the remaining. Yes, and just I think that should work. Biology, mathematics, statistics. Yeah. Now if we okay, good, we got our dataset ready. Now next thing is to create a target list, right? The target list is basically the number of labels we have, right? We have 6, so I'll just take those 6. Okay, 1 2 3 4 5 6. Yes, so yeah, I think I'm not sure. That is for later use. Okay, you will get to know how I will use this later in the implementation. So now I'm just define some hyperparameters like maximum length, train batch size, validation batch size, epochs, and learning rate. Okay, it's generally 512 in case of BERT, but I have less data, so I'll keep it as 256. Also, your hyperparameters are those parameters from on which you can play, right? So you can choose your own settings. I'll just choose the default ones for simplicity's sake. Okay, next would be train batch size. Oops, not art train, just train. Let's say 32, and valid batch size 32. Okay, epochs, I'm gonna train it on 2 for so that it shouldn't be long. Learning rate 0. Oops, not. This was mentioned on the Hugging Face website. You can check it out. Just go to Hugging Face. So this is the site you can explore more. Okay, this dataset models and all, it provides everything. Cool. So hyperparameters are ready. So next step is to import the tokenizer. Okay, so from transformers import BERT tokenizer and BERT model. So the BERT tokenizer provides a tokenizer which was developed for BERT, and BERT model is basically the BERT model. Okay, we will get our tokenizer from this one line of code. Dot from pre-train. I'm going to use the uncased BERT version, BERT base, right? Okay. There are two versions, BERT cased and BERT uncased. In uncased, it doesn't involve the casing of the letters, right? I'll just execute it. So what tokenizer does is, I'll show you an example. For example, my example text is my channel name is, or do like and subscribe my channel. Next, we will get a dictionary. Okay, encoding is equal to tokenizer dot encode plus. So this function requires a text and something of, let's say, add special tokens to max length is, let's say, max length. In padding, we want to do of the max length, and truncation is true because we don't want exceeding characters after max length, right? So we will remove those. That what truncation means. And return attention mask. PT means Pytorch, okay, Pytorch tensor. So this will generate an encodings which will be a dictionary. So I'll just show you. Add special tokens is basically that there are special tokens which are required for BERT during the pre-training and fine-tuning process. So these tokens are basically the CLS tokens and the padding token, the separation token SEP, okay, and also the mask token. Mask is not used right now because it is only used during mask language modeling pre-training process. Okay, so basically these are our three main tokenizers, special tokens. Sorry. So yeah, that's it. Okay, so we will just execute the encoding. So we got encodings. As you can see, it has got three dictionaries, three keys actually, input IDs, token type IDs, just forget about this, attention mask, and yeah, that's it. So input IDs are basically just converting do to its index, right? Okay, and like to its corresponding index, and subscribe my channel, that is it. So for example, 101 is for special token, that is classification token, the CLS token that I told you about earlier. So that is inserted at the beginning of every sentence, 101 token, okay, and then the tokenization take place, the conversion from word to index, right? So for example, do is the index, do is at the index 2079, and similarly for these, right? Okay, 102 is basically separation token, okay, whenever sentence end, the BERT itself, the tokenizer library adds a separation token. Okay, cool. The attention mask, what is attention mask? It is basically the attention mask is one where we have words, right, where the where there is not padding token, right? So there is one, and after that it is all zeros because there is because those are padding tokens. Okay, so that is what attention mask is. Wherever there is a word, there will be a one, otherwise zero. That's it. Token type IDs are basically the it calculates the difference between the two sentences. So for example, if I had another example, blah blah blah, so this is my segment 1 and this is my segment 2, okay, so it will be allotted as 0 and this will be allotted as 1. This is just for for BERT pre-processing. It is all mentioned in the paper, the research paper, you can study about it. Okay, so this is so for training we will be needing all these three tensors: attention mask, token type IDs, and input IDs for the training purpose. Okay, so this was an example. Now I will go on to building a custom dataset using the Pytorch dataset and data loader library, which is the standard method for creating the custom datasets. Okay, so you should follow all this convention basically. Okay, so next step is to create a dataset class. I'll name it as custom dataset torch.utils.data. So a constructor first, obviously we will take our df and our tokenizer and max length. Okay, we will just create class attributes tf STF. So the tokenizer is tokenizer self dot maxlen. Okay. And also self dot title. Title is basically one record, one sample, right? For example, train df 0. Oops, sorry, not 0. Context of 0. This is our title, right? And targets are basically all the outputs value. This one, only this one, right? Okay. In here I will use my target list that I mentioned above to get the values. So what this does is it basically gives us the all the array values, right? So if I'll show you what does it do. Target list what values. So this is all the array values, right? Right now we have just integers value. It converts into array value that we need for our training purpose. Okay, so we got our targets, and then we define two functions. One is length and one is get item for every dataset class, right? So we will define those. We'll just return the length. Next is get item. So we get item with the help of an index, right? For example, train df like context of 0. This index is what this is, right? So we get one example using this function, which is used in our training process. So we will get the title. We will first convert it into string, and then we will again convert it into string, right? This is basically done to ensure that our title has nothing, garbage value or something that makes it a problem while training. So now we get our inputs. We tokenize our input like I showed you earlier using the encode plus method. So self dot tokenizer. None is basically it sometimes required two strings to actually compare sentence similarity. Okay, that is another project, but we don't need the second example. We only need one. So add special tokens as true. Computation is okay. Now we will just return the inputs, right? It is a dictionary, as I explained you earlier. It consists of input IDs, token type IDs, and attention mask. So I'll just return the dictionary. Flatten basically flattens the dimension. For example, right now my inputs, this dimension of this tensor will be 1,512. The flatten converts it into 512. So this is what flatten does. Okay, and it is required for a training purpose. Next is attention mask. And the last key is our targets, which will convert it into float tensor. Float tensor, which is required for training purpose. Okay, I think our data class is ready. Cool. So this is basically used when we create our dataset using a data loader using the Torch library. Okay, this is a standard approach. Okay, we always use this kind of approach when solving classification problems using BERT. Okay, so next part is I'll just split my dataset into 0.8 and 0.2 fractions. Okay, so frame size will be, let's say, 0.8. You can play with it. Now my frame df dot, I'll sample a fraction of 0.8 samples, right? So my frac will be 0.8 and random state will be, let's say, 200, and I'll reset the index so that the index won't get messed up after resampling the rows. Next, for validation df, it's the same thing I do for validation df. Okay, so our data is ready to be created into a custom dataset class. So we'll do that. Custom dataset, train df, and tokenizer, and max length. Same we'll do for valid dataset. Okay, cool. We have created our train and validation classes of custom dataset class. Now next thing is to create a data loader. Okay, so train data loader is loader, so it requires plain data set, and I'll shuffle and batch size as plain batch size, num workers equal to 0. Num workers basically means to use all the GPUs which are available. Okay, yes. Same thing I'll create for validation data loader. Just say val data loader, and here valid data set. Oops, not valid data set. And I'll, because we don't want to shuffle the validation data set, and here valid. Okay, so we have our training data loader and validation data loader ready to be fed into our model. Okay, so before that, we will define that device which will be loading our tensors to, which should be in our case the GPU version. Okay, because we are using the GPU version of a collab. So for that, we will say torch dot device CUDA if it is available. Torch dot CUDA dot is available. I think this is the correct syntax. Else torch dot so if I print my device now, so it should say we have device, right? CUDA, right? We have CUDA. Okay, so the next step is to create checkpoints. So what will the checkpoint do is basically when we have a best accuracy, it will save the checkpoint, and similarly a load checkpoint function which will load that best load checkpoint. Okay, so I'm going to create load checkpoint. Okay, checkpoint f file path and model and optimizer. Sorry, not optimizer, it's optimizer. So now torch dot load will give me the checkpoint of this file. Okay, then I will basically load the checkpoint dictionary into the model so that it loads the last state of that model. Similarly for optimizer, sorry, it should be state dict, not that. The checkpoint basically it saves all this information like the state dict. State dict is basically the weights and biases of our model, right? An optimizer means the optimization state. And now we will get the valid loss, the minimum valid loss, right? So in the end, we will just return the model optimizer checkpoint epoch and valid loss minimum dot item. Item basically provides us the inner value, right? For example, we have this value 0.098 tensor, and it is a tensor. So dot item will return only this part, right? So we will have only 0.98. Good. Okay, so this was our load checkpoint, and similarly we will define a function which will save our checkpoint. We'll save the state of our optimizer and our model, and we will ensure it is the best one. Checkpoint path, model path. Okay, so we'll get the path, checkpoint path, and next we will just save the state in our this file path. Okay, and if it is best, we want to copy the file. Okay, cool. Now we are done with the loading and saving of our torch model history and the states, right? Next is the interesting part. Now we will be building our BERT class, right? The BERT model. So we will define a BERT class, let's say, and it will inherit our model module from torch. So after inheriting this, we should define a constructor method and a forward method. Okay, so the constructor, in constructor we will have nothing, and we'll just make it a super class. Now we will initialize the layers. First layer will be our BERT layer, the BERT model. BERT model dot tokenizer, BERT model dot from pre-trained BERT base uncased. This parameter basically returns two outputs. Okay, one is the sequence output and one is the pooler output. The sequence output is basically output of every word, right? For example, please like and subscribe. So it will, so there will be a tensor for this one, this one, this one, and this one. But in case of pooler output, there will be only an output one, only one output having dimension 1,768. 768 vectors there, and this is for the classification token. So that is the difference between the two outputs which we'll get after our BERT forward operation. So next layer would be a dropout layer. Dropout. So it will be torch dot actually mn dot dropout. Let's say I'll give it 0.3, and last layer would be a linear layer. And we have 6 classes, right? So there will be 6. And 768 basically means as I told you right now, the output layer have the dimension of 768, the BERT output layer. So that is why input will be 768 and output will be 6 classes, right? So next our init class, our constructor is done. Next function is our forward function that will take our input IDs, attention mask, token type IDs into the model and will forward it and return us the output, the pooled output. Okay, so for that we will need input IDs, tension mask, token type IDs. Okay, so output will be BERT model, and this will take our input IDs, attention mask, token type IDs. Okay, next will be our dropout output, right? Our output dropout will be our self dot dropout output. So this becomes the input to this layer, and the final output will be linear output. Self dot linear output dropout. And also make sure that this is our pooled outputs. Okay, so as I told you earlier, it is a dictionary. It contains two outputs. That is one, the sequence output and the pooler output. So we want the pooler output. So for that we need dot pooler output. Okay, so now I think we are done with the model. We'll just return the output, and we will create our model. Let's say BERT class, and we will push it to the our GPU. That is the syntax of pushing the tensors into our GPU. Let's run it. Okay, cool. We have our BERT class. Okay, so the next step is to define a loss function. So loss, so I'll be using the BCE with logic's loss. You can read more about the loss in the torch BCE with logic's loss. So you can read more about it here. Okay, loss function, it will take the outputs. Every loss function takes the output and the ground truths and the targets. So we will just return the BCE with, I think this is the correct, with, come on, give me suggestions. And here will be outputs and targets. Okay, optimizer torch dot optim dot Adam. Params will be our model or parameters, right? And learning rate will be learning rate. Yes. So we got our optimizer. Okay. Model dot optimizer got an empty parameter list. I think something is wrong. Good. So actually I forgot an underscore here, so that is why I didn't execute it properly. So now it will download the model. Now it is pushing our model to the GPU. Okay, I'll just clear the output. Okay, now we got our optimizer. The next step is to create the training loop. That is the main part of the implementation. So in the training loop, we'll require, let's say, train our model. It will require an epochs, the training loader, validation loader, model optimizer, checkpoint file path, and best model path. Okay, so we will define the minimum validation loss tracker. So basically it will track the validation loss. Okay, so initially the value should be maximum, right? So that is how it will track the minimum values, right? So for that should be the maximum value initially. So for that we have np dot infinity value. It is basically infinity value. Okay, so we will iterate through the epochs. Let's say for epoch in range 1 to n epochs plus 1. I want to start from 1 because 1 looks good. So we have our train loss, which is 0. Oops. Train loss 0 and validation loss 0 initially. And now we should put our model in train mode. Okay, so now is the training happens. Okay, the training will take place now. So for batch index and batch in enumerate, I'll just write index so that you won't get confused. Enumerate training loader, training loader. Okay, so this batch is basically, so training loader provides number of batch size number of examples first, right? Like 32. So batch will be consisting of 32 examples converted into its corresponding input IDs, attention mask, token type IDs, right? So that is our batch. Index is basically 0, 1, 2, 3 to 31, right? Because it is 0 to 31, right? 32 examples. So okay, we will extract the input IDs like I just explained. Input IDs will be our batch of input IDs, and we will push it to our device so that all the calculation and computation take place on our GPU. And we will also change the D type, which is required to the torch long D type, right? Similarly, the attention mask, and lastly we'll have our targets. Because we are in training loop right now, we won't be needing targets when we are in the validation loop, right? Because we just need to validate how good our model is performing. In case of targets, we should convert it into float. Okay, finally we will have our output as model, all this as input. Okay, optimizer.zero guards so that it won't get the graph of torch. You will all you can just go through a playlist for Pytorch, right? Just go to YouTube and search for any playlist for beginner tutorial for Pytorch. All this is required for the training purpose. This is a default, this is a general configuration, right? Like how we train a Pytorch model. So that is a general technique I'm writing here. Then we calculate the loss using our loss function we defined earlier. It takes our output and targets, right? Outside outputs and targets. And then again we set the optimizer to 0 grad. And finally we calculate loss backwards, the gradients, and make the optimizer to optimize the loss. Now we calculate the training loss. Okay, so this was our training loop. So this is all our training loop, right? So now we will get to our validation loop, sorry. So this is our we need to do it for each epoch, right? So yes, validation loop, and this is the training loop. Okay, now for evaluation and for validation we will set the model into eval mode. Now wait, this is basically done to so that it does not calculates anything in the Pytorch graph model, the weights actually. So the same thing will take place now. We will just copy on this. And we won't be needing, so this should be indented, and here it should be validation loader instead of training loader. Okay, and we won't be needing any targets here. Actually we will be, because we need to calculate the loss, right? So we'll be in the prediction, we won't be needing any targets obviously. Okay, so I have input IDs, mask, token type, targets, output. Okay, and we don't need the optimizer here, we need the loss. We don't need optimizer, just need to calculate. Okay, cool, right? And here will be validation loss instead of train loss. Okay, cool. Okay, so this was the validation loop. All right, so next we create a checkpoint dictionary in which we will be saving the best checkpoint, the best model. So valid and I'll just save the checkpoint using the checkpoint dictionary. The function I defined earlier is best, is will be false. Okay, cool. Now we will just return the trained model. Okay, cool. Now we have a training function ready. Now to train this model, I'll set a checkpoint path to say, that's right. I'll just mention the checkpoint in the function itself. Train model, and here I will be saying, let's epochs, training loader, train data loader, val data loader, and model. Okay, the model, then the optimizer. Checkpoint path will be the root directory, best will be the root directory, current checkpoint best.pt. Okay, so now I'm not going to run this because I've already trained it on 2 epochs, so I'll just keep it in the background of training. I just wanted to show you how we can implement a multi-class classifier using BERT and Hugging Face Transformers library. So let's test it on the model that we just downloaded using the BERT, right? This one, not the trained one. You can train it yourself in the meantime. I don't have the time to train it right now because I'm recording. So let's use the previous model, right? The not trained one. If we trained it, it would be performing much better than this one. Okay, just keep that in mind. So let's take an example. Let's say example will be, we had the test df above, right? So we'll be using the abstract. Okay, so what is this example? Let's see. Okay, we represent our understanding, blah blah blah. Okay. Okay, so we will be, the next step is to tokenize this sentence, right, like we did earlier. So for that we will be saying encodings, and just copy paste this one, right? We'll just encode it. Say encodings, and not title, we'll have example, and max len will be max len, and yeah, that's true. So this will return us a dictionary consisting of input IDs, attention masks, and token type IDs. Okay, with the help of which we will be um, using that into our model, the BERT model. Okay, so but with before that, we should put our model to eval mode before predicting, right? Model.eval torch dot grad. This is the basic code which is required every time, right? Just consider it as a template. So we will have input IDs. I'll just copy all this from here. Okay, I'll just, so instead of batch, we'll have encodings. Okay, now we get the output from our model. Oops, what the heck? Okay, we got the output. Okay, then we'll get the final output as, we will apply the torch.sigmoid layer on the output and convert it into the list, because right now it will be having 768 vectors, right? But we want to convert it into a sigmoid layer. Okay. Okay, print our final output. Self is not defined. Oops, sorry, just tokenizer. Okay, so we got the accuracies 54, 57, 56. So basically this is the highest, right? Okay, so we don't actually get some much information from this, like which label is what. So for that, I'll do one thing. We'll get the train df dot columns. Okay, so we don't want the context, right? So we will go from one index. Yeah, now it's good. We have 6 labels, and I'm going to convert it to list. Okay, cool. Okay, cool. But also, to get the maximum argument, to get the maximum, the index having the maximum value, we'll just use numpy argmax function on the axis 1, right? I think it should print 1, yes, because the second one is the 0.57, which was the highest one, right? Okay, 1. Now if we just do this like this, it should print physics. Okay, cool. Okay, we'll just copy this and yeah, I think that should work. Oops, print. Okay, here something is wrong. Okay, I'll just undo everything. Okay, we have print here. Okay, this should be in a square basis, and this should be int, so that we'll lose one dimension. Okay, and now we'll just, this should work, physics. Okay, so this abstract was physics actually. So cool. We have finally implemented BERT classifier for multi-label text classification. So this was all for this tutorial, and I hope you enjoyed it. And if you did, please do hit like and subscribe, and please share it among your friends. So, and also keep in mind that I have not used the trained model, right? So that is why it was showing accuracy between 50-56%, right? But if you train it on at least 20 to 30 epochs, then it will obviously provide you with more than 70-80% of accuracy. So please do train it using the code, which I will link down below in the description. Okay, so yeah, that's all. Thank you.